Hello and welcome. This is SFU Math 232. My name is Brenda Davison. We are here with section 1.3, vector equations of lines and planes. Okay, just a nice, I'm a big fan of Kandinsky, so I include this here. It's kind of quite a geometric artwork. We definitely see lines in a plane here in this artwork. Okay, Kandinsky. All right, let's first talk about the equations of lines. So the general equation of a line in R2, so you will check back with your calculus notes or something like that, you'll see that it is a set of all points that satisfy this equation where A, B, and C are constants and A and B are not zero. So let's just get an example and maybe phrase this a little bit differently. So we're going to describe a line in R2 passing through the point 1, 2 and parallel to the vector 3, 4. So let's just draw a picture of what that looks like. We have 1, 2 axes here, yeah, x and y axis, and I'm going to locate the point 3, 4, that x coordinate 3 and y coordinate. Let's just try to 4, 3, 4 like that, and I'm going to put the vector there. There. That is the vector v. And this right here is 3, 4 at the terminal end of that vector. And then we have a point also, the point 1, 2. That is x is 1 and y is 2. So we have a point right here. That is x naught. Okay. What we're asking for is describe the line passing through this point and parallel to that to the vector. So that's going to look like this. It's parallel to v and it is passing through x naught. So it's going to be, to the best of my drawing abilities, something that looks like this. So this is what we're looking for. The line, let's just make it solid. The line that is parallel to v that passes through x naught. Okay, so the way we're going to conceptualize getting a expression for that line is to imagine selecting another point on this line. Let's just call it x. So there's x, another point on the line. This x naught, let's not forget this one, we know what it is. It's 1, 2. And so then now we selected another point on the line, which we're calling x. And so then we can imagine a vector right here, like that, between x and x naught. That would be the vector x minus x naught. Put it like that, or I could put it like this, x minus x naught. That is a vector between those 2 points. And that is going to be equal to some scalar multiple of v. Okay, so v has a certain length, this length here, and then this thing has a certain length, and I'll be able to find some number that I can multiply the v by to make those 2 lengths the same. So this is for some t. Okay. Then I will have that that vector from x to x naught being equal to tv. Okay, and as x moves, like if I now take this point here and I move it back and forth on the line, on this line, the value of t changes. So let me just write down what I'm saying here. As x moves on the line, t changes. So if I look at it the other way, if t sweeps from minus infinity to infinity, x moves along the entire line, the blue line on the diagram. So then it means that I can tell you what line this is in this manner. I could say the line x is equal to x naught plus tv, where t goes from minus infinity to infinity. Okay, so what we're saying, let me just rephrase that a little bit more formally. The vector equation of a line in Rn, the vector equation of a line in Rn, we just did this in R2, but in Rn it's the same. It is the set of all points x such that x is equal to x naught plus tv. Okay, and that the set of all points represents the line through x naught that is parallel to v. And the t here is a parameter. What happens if x naught is 0? Well, that's not too difficult to plug in there. So let's just see what happens. That means that x would be equal to tv. That's what would happen. T would still be going from minus infinity to infinity. And that means we'll have a line here that is parallel to v and passes through the origin. This line passes through the origin. Okay, so what we did here is we just took a look in 2 dimensions, what's happening, and then we just can immediately generalize it and say, well, that's what we're going to mean when we talk about this in n dimensions, despite the fact that I can't draw a line in 8 dimensions for you. Okay, let's consider this example that we've got. So we've got this description of the line looking like this, where t is some scalar. And what we do is, if we're talking, now we're back into, we're just going to do an R2 example here. So in R2, the points on the line, this set of points on the line is x, y. And then our initial, the point that the line is going through is x naught, y naught. So what I'm saying here is x is x, y, and x naught is x naught, y naught. And then we have some vector v. Let me not use, I've been using this one, v. That is going to be, I'm going to just have that as the components of that vector, a and b. So I can write x, y equals x naught, y naught plus t times ab. And then I can write out the first and second line of that equation there separately, and that will look like this. X is equal to x naught plus at, and y is equal to y naught plus bt. So I could specify the line in this manner, and this is the parametric equation of the line. Okay, let's take a question here. We've got 2 lines, line 1 right here and line 2 right here. And we're wondering, do they intersect? Well, what does that mean? Do they intersect? That means they have to share a point in common. So the question really is, when this says, do these 2 lines intersect? We're saying, do they share a point in common? Okay, let's suppose that they do. Call that point x naught, y naught, z naught. Okay, because those this proposed point x naught, y naught, z naught is on both lines, it must be the case that x naught, y naught, z naught is equal to 2, 0, 1 plus r times 3 minus 1, 0 for some r. That must happen. And also x naught, y naught, z naught must equal 5, 1 minus 4 plus s times 1, 0, 2 for some s. Okay, because that this one tells you, this means if there's some r that makes this one true, then I'll be able to represent the point on the first line this way, and I will be able to represent the same point on the other line in this way if there's some s that makes this true. Those two left-hand sides are the same. They are the point x naught, y naught, z naught. So that must mean the two right-hand side points are the same. So that must mean that there is a r and an s such that this one here, I'm going to write it vertically now, 2, 0, 1 plus r times 3 minus 1, 0 is equal to 5, 1 minus 4 plus s times 1, 0, 2. Okay, so I just do a little bit of arithmetic here, and that would mean that r times 3 minus 1, 0, I've just copied that over. Then I'm bringing the one with s to the other side, so that's going to be minus s 1, 0, 2. And then I'm going to put the two column vectors that have no parameter attached to them onto the right-hand side and combine them. That's going to give me 5 minus 2 is 3. 1 minus 0 is 1. Minus 4 minus 1 is minus 5. Okay, what do I have here? I have 2 unknowns and 3 equations. So I can now solve this and find out, is there a unique solution, R and S, for this to be true? Are there infinitely many solutions, R and S, or are there no solutions? Okay, so that's going to tell me, if I get a solution for R and S, that will tell me that it is possible for me to find an R and an S at the same time, such that that point can be on both of those lines, and that means that they will intersect. Okay, so I'm going to do this in the way that we have been doing it leading up to here, and that is going to look like this. I'm going to put this linear system into an augmented matrix, so that's going to look like this: 3 minus 1 minus 1 0 0 minus 2 minus 2, and that will be augmented 3 1 minus 5. And then I will start to do my Gaussian elimination. So the first thing I'll do is divide the first row. Actually, what I'm going to do, it's going to be easier. I just momentary pause there while I thought of something smarter. Hopefully I don't flub up on the arithmetic. And that is, I will switch rows 2 and 1, and I'm also going to multiply through by -1 at the same time. So this is going to be R1 and R2 are switching, and then when I'm moving R2 up, I'm also going to replace R2, well, I'm going to replace it by the negative. So maybe I'm going to actually do this one first, and then I'm going to switch them. Okay, I'm going to be here. 1, 0, minus 1, and then I'm going to just move R1 down, -1, 3, and then row 2 there remains unchanged. Okay. And then I'm going to take R2, and I'm going to replace that with R2 minus 3 R1. So row 1's unchanged. There it is. And I'm going to subtract 3, and then 3 minus, let me think here. I'm multiplying that by 3. I get 3, 0, minus 3, and then I subtract. So this will be 6. Okay. Yeah, I'm saying 3 minus 3, minus 1 minus 0. 3 minus minus 3 is 6, and then this guy's staying the same. Okay. And then I would want to, so I've got a leading one here, so I'm going to multiply row 2 by -1. And then I have this one here. Okay, I have a leading one here. I have a leading one here, and then I'm going to see what happens with this last row. And I find that I would leave the first two rows alone. And then I'm thinking of adding 2 times row. I'm taking here, I'm going to write the operation below here. I'm taking row 3. I'm going to replace that with row 3 plus 2 times row 1. That nets me to 0 here. And I get 2 times minus 6, I get minus 12. I add minus 5, I get minus 17. So I immediately look down and I see we have a problem here. There is no solution. So there's no R and S that will make all 3 of these things true. So this is no solution. And what does that tell us? The lines do not intersect. Okay, so the lines do not intersect. All right, let's take a look at a bunch more definitions and ways of looking at lines. We just saw this in R2. So this is a parametric equation of a line in R2. We just did this. And then let's take a look at what it is in R3. Well, in R3, it is the set of all points such that x, y, z. So we've got the 3 variables now is equal to x naught, y naught, z naught plus t times v. Let's just use the v this way, v. And we have been representing v. Typically, the components of v, we've at this point been doing this, so we'll be slightly consistent here, and we'll represent v as a, b, and c. So v has 3 components. We're in R3. So here this step here, I'm saying consider v equal to a, b, and c. Okay, now I want to look at the components and write this in the parametric equation of the line. And so what I do is I write the 3 components separately, and I write that the x component is equal to x naught plus at, and the y component is y naught plus bt, and the z component is z naught plus ct. And that represents the line through this point with those components and parallel to this vector. Okay, this guy is right there. Okay, let's take an example. What is the equation? What is the vector equation of a line passing through 2 points in Rn? So let's just, draw a little picture in R2. I'm going to do this all the time because this is the way I think. In R2 or R3 at the best. That's the best I can hope for. Okay, so there is x1 and x2. So what we're wanting to do is get the equation of that line, but we're thinking about it in Rn. So what we're going to do is we're going to let v be equal to x1 minus x naught. Now we're back to the situation that we had before, and the vector equation of the line is this: x naught I'm wondering why I put minus t. Hang on, just a momentary pause here. I see something in my notes I'm not convinced I should do, and I'm just going to check. X naught plus, good, I have a mistake in my notes, t v. There it is. And what is tv? tv is x1 minus x naught. So then that means the vector equation of the line is, I have x naught, I have 1 x naught here, and I have minus t x naughts here. So that looks like this: 1 minus t x naught plus t x1. So that is the vector equation of a line passing through 2 points. Okay, question then. What happens if we change, oh, and let's be careful because I didn't even write that. So in this case, t is in, well, let's write it this way. T is from minus infinity to infinity. Okay, so that's what this means. T is in R, T is from minus infinity to infinity. Okay, what happens if we change that from T going from minus infinity to infinity, T going between 0 and 1? So let's just write out the equation. What we have here in Rn, we have x is 1 minus t x naught plus t x1. We're going to look at the endpoints. Let me just write this below with all the, looks like this. We have a couple of ways we could write this. Okay, now if 0 less than or equal to t less than or equal to 1, what happens? Let's look at the endpoints. T equals 0 would mean that x would be equal to x naught. And when t is equal to 1, x would be equal to x1. I'm simply plugging in, you can see it in either one of these two forms, but I'm writing it in this manner here, that I'm plugging in t equals 0 and looking at what happens, and then I'm plugging in t equals 1. So you have the equation of a line segment between x0 and x1. So here you have the equation of a line segment between x naught and x1. Okay, so let's do another example. What are the vector and parametric equations of the line passing through 2 points? Here we've got 2 points and we are in R3. So we've got 1 point, let's call it x naught. It is 0, 1, 1. And the second point, x1, which is 1, 1, 0. So x, the vector equation of the line passing through these 2 points in 3 dimensions, looks like this: 1 minus t times x naught plus t times x1. Let's put the numbers in for this example. 1 minus t, and what is x naught? X naught is 0, 1, 1, and then t times x1, 1, 1, 0. There we go. That's the vector equation of the line through 0, 1, 1 and 1, 1, 0. Okay, letting x be equal to x, y, z, we can write this way: x, y, z is equal to 1 minus t times 0, 1, 1 and t 1, 1, 0. And then we simply can read off the different components. Line 1 tells us that x is equal to 1 minus t times 0 plus t times 1. And that looks like t. And reading from the second line, y is equal to 1 minus t times 1 plus t times 1. And what does that look like? That t cancels out, so that looks like 1. Z looks like this: 1 minus t times 1 plus t times 0, and that looks like 1 minus t. So the parametric equations of the lines look like this. I'll just rewrite it. X equals t, y equals 1, and z equals 1 minus t. That describes all of the points on the line where t is in R. Okay, so let's just check out how we get back to 2 points. So for example, when t is equal to 0, I find out that x is equal to 0, y is equal to 1, and z is equal to 1. And that is, this thing is x naught. So for the value of the parameter 0, I get back the x naught point. And for the value of the parameter 1, I get back the point. So now I'm plugging in 1 into these parametric equations. I get x is equal to 1, y is equal to 1, and z is equal to 0. I recognize that as the point x1. Okay, and then all of the other points on the line I can get by choosing different values of t. All right, so that we were talking about lines, and now we're going to move for a bit anyways, talking about planes. So we're going to start with an example. We want to describe the points of the plane passing through a point x naught, which are perpendicular to a vector n in R3. Okay, I'm going to draw what I hope to be an illustrative example here. I'm imagining this to be my vector n. Doesn't matter which direction it's in for my example, but I find it easier to draw like this. So I'm going to draw it like this. So I imagine this vector n in R3, and then I'm going to draw a plane that is perpendicular to this vector. I'm going to draw, in fact, more than one of them. Okay, I'm going to draw 2 of them. Okay, so what I'm thinking here is this is coming, and it makes it maybe a little bit easier to see if I erase this. And then this one comes here, and this is our usual problem of trying to draw something in 3-dimensional on a 2-dimensional surface. But what I'm thinking about here is this is a right angle to the plane, and this is a right angle to the plane. So my idea is I've got this plane. I've got more than any number of these planes, but I've got a plane, and you can imagine a vertical, like stick up your pencil, say vertically, and then imagine, puncturing through your sheet of paper such that your sheet of paper, the plane, is parallel to your vertical pencil. That's what I've drawn here. I think I could probably adjust the angle on this one. It might be a little bit better. Let me just, I think I'll adjust it a bit. Okay. Okay, so and what we have is there's many planes, infinite supply of planes that are perpendicular to n. So here we are, plane. We got this here right now. We've got a plane. We don't have the passing yet. We have the plane perpendicular to n. We've got a whole bunch of them. Now, on one of these planes will be the point x naught. Let's think that it might be this one. There it is. So x naught is here. So x naught is choosing amongst this multitude of planes. X naught is picking out this specific one. That specific plane is the one that is parallel to n, and the plane passes through the point x naught or contains the point x naught. There is only one. I mean, of all the ones that I have, only one of them is going to be the one that has x naught on it. Okay, so the perpendicular. So you notice we use this n. This is going to be typical. N is normal. That's why the n is there. Normal to the plane. And that means at right angles, orthogonal, perpendicular, those words that we can use for that. Okay, and so then what we're going to do here is we are going to imagine another point on the plane. Let's just call it x. There it is. We imagine another point on the plane. We call it x. And then I can connect these two as a vector. There's a vector joining x and vector coming right here to the point x, and there it is. Now, we know that when two vectors are orthogonal, that their dot product is 0. So it must be the case here that the normal vector dot product with the difference of those two vectors must be equal to 0. Okay, so let's take a specific thing. We've got a specific point, x naught, y naught, z naught. We've got a normal vector with components capital A, capital B, capital C. And then we select this other point, x, y, z, and we write this this thing here, the normal vector dot product the difference between x and x naught, which looks like this, x minus x naught, y minus y naught, z minus z naught, is equal to 0. That, what I've written there, is called the point normal equation of a plane through x naught with normal n. Let me write that out a little bit further. Okay, I'm performing the dot product operation. Okay, so this right here is called, this one right here, this is called the point normal equation of a plane through x naught with normal n. Now I can simplify this a bit by simply multiplying this out. I'm taking this and distributing the a, b, and c. So I get ax minus ax naught plus by minus by naught plus cz minus cz naught equal to 0. And these things are simply constants. They're just numbers, and they're known. So I have here then ax plus by plus cz is equal to ax naught plus by naught plus cz naught. And I'm going to add those three things together and call that d. And then I have this, ax plus by plus cz is equal to d. That is the general equation of a plane. So you can see now where the general equation of the plane comes from. Again, we ask the question, what happens if x naught is 0? And that would mean that, well, we still have the same formulation, that the normal, take the dot product of the normal and x minus x naught, that will be 0 as it was before. But now we've got, if x naught is equal to 0, then this becomes n dot x is 0. And that, when I write it out in the general form, equation of a plane, that looks like this, ax plus by plus cz is equal to 0. So that is a plane that goes through the origin. So let's just take a look about what happens, the general equation of a line in R2. What does that look like? Ax plus by equals c. You're used to that from high school or from calculus. And then the general equation of a plane in R3 looks like this. Ax plus by plus cz is equal to d. We've just scaled up by one dimension. So let's do an example in R3. Here's our normal, normal with normal minus 1, 2, 1. And here is our point. Yep, through the point 1, 1, 2. So we want to write the point normal equation of the line. So that is now easy to do. So I'm gonna write it out right from the thing we have here in the terms of, this is a, this this is a, this is b, and this is c. Okay. in our normal vector. So I can easily write the point normal form. It looks like this: minus 1 times x minus 1 plus 2 times x minus 1, sorry, y minus 1, plus 1 times z minus 2, and that is equal to 0. So this is the point normal form. Okay, and then I can simplify this algebra. Why don't you do that as an exercise as well? Check if I didn't make a mistake. I got this: x minus 2y minus z is equal to minus 3. So let's see. Does that look right? I've got. Oh, I see. I did it. Or it could also look like this: minus x plus 2y plus z is equal to 3. That's another possibility. There's a general equation. It doesn't matter if I multiply both sides by minus 1 or not. So let's think, does that match up? I see the minus 1, 2, and 1 here. The normal vector there. Okay, so this is looking pretty good. Then I can't quite as easily see those. Can I see those constants as easily? No, not quite. I have to do the arithmetic and make sure that this 3 is the right number. Okay, so that is either one of these things here is the general equation of the plane through the point 1, 1, 2, perpendicular to the vector minus 1, 2, 1. Okay, so here, let's do the reverse problem. We're given an equation of a plane in R3, and we're asked to describe it. So I look at this, and I see the 0 here, and I feel happy about that because I can hang on a sec. Oh no, I don't necessarily feel happy about that. It's okay. I almost said something wrong, but luckily stopped myself in time. So no, I just disregard that last little comment. What I'm looking at this now, it's the equation of a plane, that's for sure. It passes through what point? So okay, I'm going to start writing. This is the equation of a plane which passes through the point x naught is equal to 3 minus 2 and 1. Okay, I'm looking here, here, and here. Now, this point is for sure on that plane, because look, when I put that number in, 3 minus 2, 1 into there, I get 0 equals 0. So that point is certainly on that plane. And the plane is normal or perpendicular to the vector n, which is 1, 2, minus 3. Okay, and that is those numbers sitting outside here: 1, 2, minus 3. Very good idea as you're working through this stuff to try to draw yourself pictures in two dimensions and possibly in 3 dimensions, and then allow it to generalize and sort of believe and or prove to yourself, depending, that it continues to work as the dimensions scale up and we cannot draw it any longer. Okay, let's take a slightly different view. Let's try to see if we can figure out what the points, if we can describe the points on the plane passing through the point x naught and parallel to 2 vectors that are not parallel in Rn. Okay, first let's just try to sort out what the question is asking us. I'm going to draw a plane. Here's my plane. And I'm going to draw a perpendicular vector to the plane. So it's maybe going a little bit too far down. So I'm here, and then It's coming out here. So this gives the idea that this plane is perpendicular to this vector. And I've got a point on the line, a point on the plane. That is x naught. I'm given that. And I have two vectors that are not parallel that that this plane will be parallel to. Okay, so those vectors have to be in the plane. Okay, we can have other plane here. I'm just going to draw this. There's v1 and there's v2. So I've got two vectors that establish where the plane is, and then there could be other ones that are parallel. Here, let me just draw another one. I could easily have another plane here, okay, like that, with those same two vectors. And that vector would also, those two vectors would also describe a plane, but that plane would not contain x naught. So this plane here, let me just circle where, x naught is here. This plane here, tick, contains x naught. This plane does not. This plane is parallel to the vectors v1 and v2, but it does not contain the point x naught. So we get a unique specification here. This plane here is uniquely specified by v1, v2, and x naught. All the other planes that are specified by v1 and v2 are parallel to this one, but they don't contain x naught. So how do we go about describing these points? Well, we do the same thing. We're going to select some x here in the plane. Okay, and then we will have that x minus x naught is going to be some linear combination of v1 and v2. Okay. I imagine x to be here, and then I think, okay, so I would have to maybe come along a little bit here, v1, and then I would be able to come on v2. So basically moving in the direction of v1 or v2 by some amount, some multiple of v1, and then some multiple of v2, I will be able to get to x. And then this line right here is x minus x naught. So I can form that line x minus x naught as a linear combination of v1 and v2, and then I can rewrite that easily as x equals x naught plus t1v plus t2v2. This should be v1. And independently, I will allow t1 to range from minus infinity to infinity, and t2 to range from minus infinity to infinity. So this right here is this calculation I can make here with any values that I want of t1 and t2 will give me this vector x coordinates x, y, and z that will give me all points on this plane. And the plane doesn't just end right here either. This is an infinite plane. Okay, I just can't draw that, but so this is a plane that keeps going indefinitely. That is the vector equation of a plane. So we can write it parametrically as well. So we imagine x to be like this, x, y, z, and then that is equal to x naught, y naught, z naught, plus t1 times v1, a1, b1, c1, plus t2 times a2, b2, c2. Not sure if I said A2 or T2 here, but that's a T2. Okay, and then we can read off that top line. So I'm reading off the top line here. That is the x coordinate will be x naught plus A1 T1 plus A2 T2. And then I read off the second line, and I get that y is equal to y naught plus B1 T1 plus B2 T2, and similarly I get that z is z naught plus C1 T1 plus C2 T2. That is the parametric equation of a plane, and this plane is parallel to V1 and V2, and it goes through the point x naught. Okay, let's take an example here. We're going to try to find the equation of a plane, and it passes through 1, 2, 3, and is parallel to V1, 1 minus 2 minus 1, and V2, which is 3, 4 minus 2. Okay, so V1 and V2 are not 0, and they're also not parallel themselves. We need to have 2. Think about why that is. If V1 and V2 were just scalar multiples of one another, would you be describing a plane or not? Okay, so I'm going to write the equation of this thing here. It looks like this: 1, 2, 3 plus T1, 1 minus 2 minus 1 plus T2, 3, 4 minus 2. And again, T1 and T2 vary from minus infinity to infinity. Okay. That is the equation of the plane that passes through 1, 2, 3 and is parallel to those two vectors. Okay, our last slide here, we're going to do the same thing. We're going to try to find the vector and the parametric equations of the plane, and passing through 3 points. And I'm going to point out that these are not collinear. These are 3 non-collinear points. Okay. That means that they're like these 3 points are all not on one line, because if these 3 points were on one line, imagine what that would look like. You imagine 3 points on a line like that there, and imagine how many planes you could put through there. You could put through an infinite supply of planes through there. This would sort of look like well, I mean, so planes would be, you could take a plane through all of them. That would be right here like that. And then you could imagine just rotating this thing around that line. Every single one of those planes would be containing those 3 points. So we're going to consider them not collinear for the purpose. Well, they aren't collinear in this example, but so if they are collinear, that's you don't have a unique plane specified. Okay, so let's look at let's name these points that we have. We're going to call the first point x naught. That is 1, 0, 0, and y naught, which is 0, 1, 0, and z naught, which is 0, 0, 1. So what we're wanting is the equation of the plane that goes through those 3 points. Okay, I'm going to just draw a little bit of a picture of what this looks like. So we're going to just imagine our coordinate system here: x, y, and z. We have 3 points. We have x naught, and this coordinate is here 1, and we have y naught here. So this here is x naught, this here is y naught, and this one here is z naught. Okay, and all these things are 1. And then we imagine this plane here. Okay, so this plane is not going through the origin. It is out from the page, and it is at 45 degrees to each one of the axes, each of the 3 pairs of axes here that you can form by. Okay, so we've got this, and we've got this pair, and we've got this pair. Okay, and the plane cuts each one of those at 45 degrees, and it is lying on the front there. We're trying to find out what the equation of that plane is. That's the goal here. Okay, so what we're going to do is we're going to form 2 vectors. Okay, vector 1 is going to be x1 minus x naught. Oh no, now I called them. All right, I have to, sorry, let me change my, let me try this again. So yeah, so sometimes I call this one, sometimes I've called this one x1 and this one x2. Right now I did not. So let me just, let me be keeping with my notation that I use. So the first vector I'm going to form is going to be y naught minus x naught. Okay, where is y naught minus x naught? That is the vector right here. That is y naught minus x naught. Okay, then we want to form a second vector, and that is going to be v2, and that is going to be z naught minus x naught. Okay, that is z naught minus x naught, and that is going to be this guy here. Okay, and then we've got still this point here, x naught. So I will actually make those calculations. I will get the actual numbers. So let me get here v1. That is going to be y naught 0, 1, 0 minus x naught 1, 0, 0, and that is going to be minus 1, 1, 0. And then I'll calculate v2. That is going to be z naught 0, 0, 1 minus x naught, there it is, and that is equal to minus 1, 0, 1. Okay, so now actually I'm back to where I was before. I have two vectors. I want the plane that goes through a point and two vectors. I already know how to do this. So the plane, I can describe the plane in this manner. X naught plus T1 V1 plus T2 V2. Okay, and in this particular case, that looks like this. 1, 0, 0 plus T1 V1 plus T2 V2. Okay, so we have the idea. We started in R2. We had the vector and parametric equations of the line in R2. Then we moved to R3, and we have the vector and parametric equations of the plane in R3, and we just simply generalize that up. So we generalize the idea of the line, which was in R2, and the plane, which was in R3, and we generalize to n space. Okay, so we have the idea of the vector equation of a line, and we have a vector equation of a plane. So what we do is we simply take x naught, which is a vector in Rn. So it's not in 2 or 3 dimensions now, it's in n space. We take v, a non-zero vector in Rn, and we define the line through x naught parallel to v to be the set of all vectors x equal to x naught plus tv. And t is allowed to go from minus infinity to infinity. Okay, then that is the vector equation of a line, And then we have the vector equation of a plane, x naught as above, a vector in Rn. And then we have two vectors, v1 and v2, non-zero vectors, not scalar multiples of one another. Then effectively just have one. And we define the plane through x naught parallel to v1 and v2 to be the set of all vectors x in Rn, like this, where x is x naught plus t1 v1 plus t2 v2. And that t1 can go from minus infinity to infinity. T2 can also range from minus infinity to infinity. Okay, so a careful look at, and maybe a slightly different look at how we're going to talk about lines in 2 dimensions and 3 dimensions for that matter, and planes in 3 dimensions, and then how we're going to just allow that definition to just expand up into as many dimensions as we like. All right, that is all for section 1.3. See you later. Bye.